everyone, I'm Kyungtae. In this talk, I'll be presenting our paper FuzzUSB, Hybrid Stateful Fuzzing of USB Gadget Stacks. USB is the most common data communication protocol for peripherals and smart devices. It is a versatile and prevalent protocol for serial device interface, and recently, the emergence of a new USB port connector Type-C allows USB to have additional functionality like advanced power delivery and non-USB video data. So USB is essentially a communication between USB host and USB device. So once the USB device is plugged into the host machine, USB host initiates USB connection and establishes the communication channel, and then fully control the following data exchange, whereas USB device operates like a peripheral. USB host has its software stack, which is called USB host stack. Likewise, modern USB device like a smartphone has its own USB stack called USB Gadget stack. Here I'd like to briefly introduce both USB stacks. In the USB host stack, there is a physical layer at the bottom called USB host controller, which physically delivers USB data. Right above that, corresponding host controller driver directly communicate with the controller. In the middle, USB core bridges between higher and lower layer in the USB host stack. On top of that, there are multiple USB host drivers, so different host drivers provide different functions depending on what device is connected to the host. And there is an application layer at the top. USB Gadget stack on the right looks similar, but instead of host function, they provide gadget-specific functions, and each layer in the gadget stack corresponds to the same level layer in the host stack. So let's take a look at an example of USB gadgets on Android. So in USB device mode, Android supports multiple USB gadgets such as MDP and MIDI, which are all implemented in the corresponding gadget drivers within the Android USB gadget stack. So when Android mobile device is plugged into the host computer, like the screenshot on the right, users are allowed to choose a particular USB gadget that they want to use. Such various USB gadget functions are implemented in the USB gadget software stacks, and from security perspective, it has a large attack surface and could be easily vulnerable and severe when being exploited. So here I'll be talking more about USB security. In particular, we observed the goal of modern USB security is to make the USB host secure. So they try to defend USB host by detecting and preventing malicious input that are coming from USB device. Likewise, existing USB fuzzers are designed to find vulnerabilities within USB host stacks, which prevent malicious USB device from compromising and exploiting them. So in their both threat model, USB device is the one who behaves in a malicious way, providing unexpected input for exploitation on the USB host. Such an assumption sounds reasonable considering recent real-world attacks from USB device, like a bad USB, but meanwhile, securing USB gadget stack is left behind, even though it is possible for USB host to be malicious. So in this work, what we are going to do is the other way around. Our goal is to make USB gadget stack secure through fuzzing technique. There have been recent studies showing security concerns and real attacks on USB device. So they show that attackers are essentially able to unlock the lock screen through USB connection, and then they have access to private information in the victim's smartphone. This clearly shows malicious USB host is a real threat, and USB gadget device should be secure against that. Other than such a security issue, we particularly focus on two features of USB communication from the gadget's perspective. so that we design fuzzing technique for USB gadget stacks much better. First, USB gadget has multiple input channels, so it takes inputs from USB host as well as its application side. Second, USB gadget operates in a stateful way. To be specific, USB gadget works based on the state change, and in each state, it requires different input value to move on to the next state. So if any of these two features is not considered, then our USB gadget fuzzing is going to be shallow and unable to perform all the gadget functions. Based on these observations, we present FuzzUSB. FuzzUSB is the first USB fuzzing technique designed for USB gadget devices to the best of our knowledge. It realizes state-guided and multi-channel fuzzing for USB gadget software stacks. FuzzUSB maximizes its fuzzing coverage by taking inputs from the host and application side, assuming they both can be malicious. And its mutation is guided by extracted state machine and mutation rules. FuzzUSB comes with several key components. First, state machine is the one that guides our stateful input mutation. It is built using program analysis before fuzzing execution. Second, FuzzUSB uses a state coverage tracking method that is suited for our state machine-based mutation. Mutation rules allows users to adjust stateful mutation strategy in detail. An actual mutation is done guided by state machine and mutation rules, and mutated inputs will be delivered into appropriate input channel. We build a custom state machine from USB gadget code, so our state machine is focused on representing stateful behavior of a USB gadget. Particularly in our state machine, state and transition are related to program points where input is taken from input channel, so that we make the whole state machine fully controllable by our fuzzing inputs. We call such a program point transition point, and we do extract the state machine using program analysis techniques. Here I'm going to walk through an example of a state machine extraction. From the entry point of USB gadget code, we do symbolic execution until either transition point or termination is encountered. And we solve the symbolic constraint to obtain input value of each state transition. And we repeat this for every transition point. So as a result, there will be a set of transition paths. And we merge all of such a partial path into a single state machine. Instead of code coverage tracking, FuzzUSB uses state and transition coverage to facilitate the state machine-based mutation. So we define two coverage tracking methods. State coverage shows whether given states are explored or not. And transition coverage presents the coverage of explored state transitions. Transition coverage might be useful to increase fuzzing coverage because our state machine is bidirectional, but for flexibility, we leave this for users to decide. For stateful fuzzing, FuzzUSB provides some flexibility of state-aware mutation by allowing users to choose detailed mutation strategy. To do so, we define 4 mutation rules. First, users are allowed to specify state transition interval so that they can stay in a state for a given time. Second, users are allowed to pick either state or transition coverage for its state coverage tracking. Third, users are allowed to specify its preference for the next state if there are more than one state that the current state can move to. Lastly, users are allowed to react when transition fails. In this step, we generate and mutate the stateful input, which is fully driven by the state machine as specified mutation rules. So input could be generated toward unexplored states or transitions, so we would cover and execute more functionality of the target USB gadget. Then the generated input will be delivered to the appropriate input channel, which is specified in the state machine as well. Here I will walk you through how our stateful mutation works. Essentially, the mutation is based on the state machine and mutation rules. So let's assume the current state is S2. So now we're going to generate stateful input to trigger state transition from S2. So we trigger a state transition after 3 seconds according to the mutation rule R1. To this end, we refer to state machine table and figure out the next state could be either S3 or S4. We decide to take S4 as the next state because unexplored state is preferred according to the mutation rule R3 and R2. So now we know the next state is S4. In order to move to S4, we refer to the relevant entry of the table and generate the input value right and deliver that to the input channel number 2, and then the state transition will happen right away. If the transition fails, we retry this transition according to the R4. We implement FuzzUSB prototype based on well-known kernel fuzzer seeds color. In particular, we customize the seeds color to make it work for USB gadget stack fuzzing. For underlying USB device controller, we rely on virtual connection using dummy UDC kernel module, which implements a software bridge between USB host and USB gadget at the UDC driver layer. We use clear for symbolic analysis for state machine generation, and for bug detection, we use known kernel memory sanitizers such as Kasan. For evaluation, we use 28 gadgets that are coming from the latest Linux and Android kernels. We conducted prior experiment using 16 different combinations of mutation rules, so that we used a fixed rule set for the rest of the experiment, which produces the best coverage result. Based on the implementation and experimental setup, we run FuzzUSB for the given target USB gadgets. In the meantime, we found 34 new security bugs. Out of them, 27 got confirmed and 10 got fixed by the corresponding community. With high security impacts, we have gotten 8 CVEs. We evaluate the code coverage enhancement of USB gadget stack. To highlight the effectiveness of the FuzzUSB's features, we additionally define 2 gadget fuzzers and compare the result. First, GFuzzer is a baseline gadget fuzzer that does not know about both state guidance and multiple input channel. A FuzzUSB SL is a stateless version of FuzzUSB, so it disables the state-guided mutation, but multi-channel input mutation remains. The result is FuzzUSB showed 3 times improvement over the GFuzzer in coverage and showed 2 times better coverage over FuzzUSB SL, which implies multiple input channels and stateful input generation are essential for USB gadget stack fuzzing. This is a buggy example happened in USB accessory gadget. As you can see, a pointer of a global variable is assigned in thread 1, and then it is freed in thread 2. Without the validation check of such global variable pointer, the thread 1 tries to access invalid global object and causing memory corruption. Such a bug in deep state path is more likely to be triggered by FuzzUSB because FuzzUSB provides a multi-channel input and stateful mutation to reach this code. Even though we cover whole USB gadget stack, we rely on particular UDC driver for virtual connection. To fuzz more UDC drivers, we need to emulate corresponding UDC hardware. And we extend FuzzUSB to cover FreeBSD USB gadget stack but to be more scalable to closest USB gadget stacks, we need to handle more issues like state machine extraction without source code. Lastly, we used a fixed mutation rule that has shown the best coverage result in our prior experiment, but the best rule set may depend on USB gadget. Different USB gadget could have different best rule set. We leave that for our future work. So FuzzUSB is a stateful and multi-channel USB fuzzing that is designed for USB gadget device. FuzzUSB has found 33 unique security bugs and assigned 8 CVEs. FuzzUSB also shows better code coverage and bug finding skill compared to baseline USB gadget fuzzers. And we open source FuzzUSB in this repository. Thank you for your attention. To advertise myself, I will be on the job market this year looking for a faculty position. Thank you.
Kyungtae, can you hear us?
I can hear you clearly. Can you hear me?
Yes. Good.
Good.
Now we have time for questions. Anybody? Let me get started. So can FuzzUSB be applied to other platforms such as Windows? And are there any challenges if you do that?
Thank you for the question. Well, other than just Linux and Android USB gadget stacks, we have extended FuzzUSB to couple more USB gadget stacks, such as FreeBSD already. And in our evaluation, it showed good performance for sure. So if you're thinking about extending to more USB gadget stacks, like it's not open source, then we could think about more issues. For example, FuzzUSB essentially requires a source code to extract the state machine, but Windows USB gadget stack is not. Source code is not available, so we may need to think about some other way to extract the state machine. And you may need to emulate some other UDC hardware, and etc. So we need to think about that kind of technical challenges. I hope. Yeah.
Cool.
That's it.
Any other questions? Okay, one more follow-up. So you looks like FuzzUSB, the key contribution is those state awareness, and why the existing approaches they didn't notice this? So any insights on this stateful fuzzing?
Thank you for the question. As I explained in my presentation, we are the first USB gadget fuzzing, and there have been the existing USB fuzzing effort. They are a USB host version, not gadget version. And yes, we brought up a couple of challenges and motivation like statelessness and multi-channel fuzzing, multiple input channels. So existing USB fuzzers, existing USB host fuzzers. USB is basically interactive protocol. So USB host and USB gadget should operate in a stateful way. So meaning that USB host also operate. It has a statelessness. So existing USB host fuzzers, they do not actually focus on like improving the fuzzing coverage of a whole USB stack. They focused on some other issues like hardware emulation, like to implement a malicious USB device or some other USB host fuzzers. They are particularly designed to fuzz some initial step of USB communication out of the whole USB communication. So there is a difference. So we could focus on our USB gadget fuzzing is focusing on the two challenges to features.
Yeah, makes sense. So I think Kongwei has a question.
Yonghee from University of Virginia. Nice to meet you. And I have one question that you have way more blocks covered because of those leveraging all these stateful. And I kind of assume that a lot of bugs that you find new is just because of those stateful. Can you comment on those blocks that you covered more, essentially actually attribute to find more bugs? And are they all, are all bugs you find new are because of your stateful exploration, or there are some, other reasons that you can find more bugs?
Well, actually, I think I haven't covered all the evaluation step in my presentation because of limited time. But in our evaluation, you can see the how each feature of our technique contributes to the whole overall performance, like code coverage. So we can see that, or I can say that there's big difference between, among the different baseline in our fuzzing technique. We just enable that, we increment, enable, and disable each feature of our technique. Statelessness and multi-channel input. So you can refer to our paper for more detailed question, for more detailed information. We found 32 new vulnerabilities, and we cannot say that most are found by our statelessness or multi-channel fuzzing, but I guess half of that we find by our feature, our challenge solution. So yeah, I hope that answers your question.
I think it would be really interesting to see, what was the reason, and then how we can go further, because some techniques may be more effective than the others, may have different techniques, have different combination that can find more bugs. Thank you so much.
Thank you.
All right, let's thank Kyungtae one more time.